Welcome back to The Explainer. Today we're diving into something really fascinating, the Odyssey UAV. But we're not just looking at the carbon fiber and hardware. Nope, we are going to project a sort of holographic deconstruction of this machine right down to its underlying mathematical DNA. You see, every single drone in the sky is bound by the strict laws of physics, and today we're unpacking the exact computational matrices that allow this specific aircraft to conquer gravity. We've got our system diagnostics initialization queued up. Here's our flight path for today. First, we'll look at the Odyssey UAV digital blueprint. Then, decoding the drag matrix, followed by generating the lift vector. From there, we hit power and propulsion dynamics, and we'll wrap it all up with the flight envelope and performance. Let's get into it.
Section 1. The Odyssey UAV digital blueprint, the core simulation matrix.
Okay, let's dive right into this. I know, it looks like a massive list of aerodynamic jargon, right? But think of this as the genetic makeup of the Odyssey UAV. These values aren't just random math. They are the specific parameters, from skin friction to stall speed, selected to guarantee this exact aircraft shape can handle its flight profile. It details everything from how slippery it is in the air to the exact speed required to keep it from literally falling out of the sky.
So why these specific numbers? Well, they were carefully calculated and verified by advanced computational fluid dynamics analysis, specifically using a program called AVL. Engineers chose these exact parameters because the Odyssey isn't just up there flying around for fun, it has a very specific job. It has to carry a highly critical 14-pound payload. The Vortex lattice method inside that software ensured that every single value we're looking at optimizes lift specifically around carrying that heavy payload.
To do that, we have to start with the environment. 0.0024 slugs per cubic foot. In aerospace, a slug is simply a unit of mass, and this specific number represents the standard air density right at sea level. The Odyssey's entire matrix was calibrated for this baseline thickness of air. It's the physical environment our digital simulation absolutely has to conquer.
Section 2. Decoding the drag matrix, resistance in the system.
Moving into the forces actively fighting against us, first up is the zero lift parasite drag coefficient, sitting at 0.0184. To put it simply, even if the drone isn't actively generating lift, the sheer viscosity of the air creates resistance. This number is the baseline aerodynamic friction the drone faces just by existing in the airstream. For the Odyssey, 0.0184 is actually impressively low. It shows the engineers intentionally selected a super sleek fuselage and landing gear profile to minimize wasted energy as it pushes forward.
Drilling down even further, we get to the skin friction coefficient. This tiny decimal, 0.0055, represents the physical struggle of the air literally grabbing onto and passing over the vehicle's surface. It's so low because they specifically utilized ultra-smooth composite materials for the outer shell. It's a highly deliberate choice, so the air molecules just slip right past with minimal microscopic resistance.
And this brilliantly illustrates the raw mathematical blueprint dictating those exact drag and lift coefficients. Notice how dynamic pressure, which factors in that baseline air density and speed we just talked about, forms the denominator of these equations. Drag and lift aren't just arbitrary numbers. They're intrinsically linked to how fast you're flying and how thick the air is. It's all connected in this giant puzzle.
Now this one is super interesting. Span efficiency, or ED, is set at exactly 0.5. In a perfectly ideal mathematical world, an elliptical wing has an efficiency of 1.0. But in the real world, we strap on bulky fuselages, sensor payloads, and pusher propellers, and those totally disrupt the airflow. Setting this efficiency to 0.5 acknowledges this severe real-world aerodynamic interference. It's a calculated sacrifice engineers made specifically to accommodate that heavy 14-pound payload.
All of this brings us to induced drag. As the wing produces lift, it creates these swirling tornado-like vortices at the wingtips, which we map mathematically using these K factors. For the Odyssey, we have a higher order effect, K3D, at 0.0735 and a primary drag due to lift factor, K1D, at 0.0245. But notice the camber effect term, K2D, it's exactly 0. This tells us the wings have a highly symmetrical aerodynamic profile, so there's no asymmetric drag to constantly correct for. Combine these, and you get an overall induced drag penalty, KD, of 0.0980. That right there is the mathematical cost of lifting the payload.
Section 3. Generating the lift vector, defying gravity. Let's see how this all builds.
The absolute peak lifting capability of this aircraft shape is represented by the max curve slope, which is 1.06. This is the absolute ceiling of our lift matrix. Engineers explicitly targeted 1.06 because it gives the Odyssey just enough aerodynamic grip to maneuver and loiter at lower speeds without the airflow separating. If you push beyond this curve, you hit an aerodynamic stall and gravity takes over entirely.
Section 4. Power and Propulsion Dynamics, the Engine Matrix.
All right, we have our airframe. We've mapped the drag, we've got our lift curve. Now let's inject raw mechanical energy into the simulation. On the left, we have a total engine power of 9.80 horsepower. But on the right, the total power actually available to the aircraft drops to just 6.86 horsepower. When you pit those against each other, it immediately begs the question, where in the world did that missing 2.94 horsepower go?
Now, what's really interesting about this slide is it solves that exact mystery. The answer is propeller efficiency, set at 0.70. You see, propellers aren't perfect. As they spin, they experience their own slippage and drag in the air. So engineers selected a prop that successfully converts 70% of that raw 9.80 engine horsepower into usable forward thrust. It's an optimal balance for this specific design. And that missing 30%? That's just an unavoidable physical loss to the air as the blades slice through it. Section 5. Flight Envelope and Performance. Simulation Results. Time to finalize our holographic reassembly.
81.40 feet per second. That translates to about 55 miles per hour. When you calculate all the specific drag coefficients and power metrics we just decoded, the matrix spits out this number as the absolute optimal cruise velocity for the Odyssey. This is the sweet spot. It's exactly how fast it needs to fly to maximize battery endurance while hauling that 14-pound payload. But contrast that cruise speed with this one, 57.20 feet per second. This is the stall speed. It is the absolute floor of our flight envelope. If the drone drops below 57.20 feet per second, the wings simply cannot generate enough lift for the vehicle and the payload, and gravity wins. Engineers purposefully shaped the wing's curve to keep this stall speed far below the 81 foot per second cruise speed, giving the drone a really nice, wide, and safe operating window.
So, the crucial point is this final number right here, 18.8, the maximum lift-to-drag ratio. Simply put, for every 1 pound of drag pushing backwards on the drone, the Odyssey generates 18.8 pounds of lift pushing upwards. This is the ultimate efficiency score. It proves that the 9.8 horsepower engine, the deliberate 0.5 span efficiency, the smooth composites, all of it comes together perfectly to create a vehicle highly tuned for its mission.
As our holographic model completes its final upload, it leaves us with a pretty inspiring thought. Software like ABL and these digital blueprints aren't just for, analyzing spreadsheets. They are actively shaping the future of autonomous flight. From balancing massive payloads to navigating complex environments, what new aerospace frontiers will these computational matrices help engineers conquer next? Keep that in mind the next time you see a UAV seamlessly cutting through the sky. Thanks for joining me on this explainer. Keep learning, and I'll catch you in the next one.